Hi everyone, this is Alex from Made Intuitive, and today I'll be explaining the formulas in the Topic 1 Number and Algebra SL and HL section of the IB Mathematics Analysis and Approaches formula booklet. What you're seeing right now is the IB Maths AA formula booklet, and you'll be given this for all of your exam papers. I promise that if you take the time to follow along with the series, all the formulas here will start making much more sense. The formulas I will be covering today are on the screen right now. So without further ado, let's get started. The first formula is the formula for the nth term of an arithmetic sequence. We know that an arithmetic sequence is a sequence whose difference of every two successive terms is a constant. If we call the first term of such a sequence u1 and the common difference d, then we can see that un equals u1 plus n minus 1 d. For the sum of n terms of an arithmetic sequence, the trick is to rewrite the expression for Sn, except this time from the back, starting with un. If we add these two equations together, we get the following expression. Now, note that u2 is u1 plus d, and un minus 1 is un minus d. This means that u2 plus un minus 1 is equal to u1 plus un. In fact, u3 plus un minus 2, un minus 2 plus u3, or better so, any sum of form ur plus un minus r plus 1 will equal u1 plus un, given that r is any integer between 1 and n. Let's see how. From the nth term of an arithmetic sequence formula, we know that ur is equal to u1 plus r minus 1d. Also, un minus r plus 1 equals u1 plus n minus rd. Knowing that n minus r plus 1 minus 1 is still equal to n minus r, we can manipulate this equation to get the following. And since u1 plus n minus 1d is equal to un by the nth term of an arithmetic sequence formula, we get that un minus r plus 1 equals un minus r minus 1d. If we now add ur with un minus r plus 1, we get u1 plus un. So all these brackets are equal to u1 plus un, and since we have a total of n brackets, we get that 2Sn equals u1 plus un times n. If we divide 2 on both sides, we get Sn equals n over 2 times u1 plus un. Finally, we can express un in terms of u1, n, and d. So once we substitute it in, we get Sn equals n over 2 times 2u1 plus n minus 1d. The next formula is the formula for the nth term of a geometric sequence. We know that a geometric sequence is a sequence whose ratio of every two successive terms is a constant. If we call the first term of such a sequence u1 and the common ratio r, then we can see that un equals u1 times r to the power of n minus 1. For the sum of n terms of a geometric sequence, we are going to begin by expressing each of the terms in terms of u1 and r, using the formula for the nth term of a geometric sequence. Next, we are going to write down the equation for r times Sn. If we subtract the second equation from the first, all the terms will cancel out except for u1 and u1 r to the power of n, leaving us with Sn minus r Sn equals u1 minus u1 r to the power of n. If we divide both sides by 1 minus r, we get Sn equals to u1 minus u1 r to the power of n over 1 minus r. We can further factor out u1 to get the following, and multiply -1 to both the denominator and numerator to get u1 r to the power n minus 1 over r minus 1. Note that to use this formula, r cannot be equal to 1 because when r equals 1, the denominator 1 minus r and r minus 1 would be 0, and Sn would be undefined. Instead, when r equals 1, use the formula Sn equals u1n, as a geometric sequence with common factor 1 is simply a sequence where all the terms are equal to the first term. The next formula deals with compound interest. If the number of compounding periods per year is k and the nominal annual rate of interest is r%, then the rate of interest for each of the compounding periods is r over k%. In other words, at each compounding period, the value changes by a factor of 1 plus r over 100k. And since there will be a total of kn compounding periods during the n years, the future value after n years would be the present value times 1 plus r over 100k to the power of kn. This formula gives us the relation between exponents and logarithms. A logarithm, as we can see, is a way to represent the power to which a fixed number must be raised to produce a given number. You might notice that there are three conditions next to the formula above: a greater than 0, b greater than 0, and a not equal to 1. Let's find out why these conditions were put in place when dealing with standard exponents and logarithms. Firstly, if a is less than 0, b, which is equal to a to the power of x, will not be a real number for any non-integer values of x. For example, enter -2 to the power of 2.5 in your calculator, and you will get the value 5.656854 ... where I here refers to the imaginary number that is equal to square root of -1. Higher level students, you will have a chance to learn more about this when we go over the HO only section of topic 1. Next, if a is equal to 0, b is equal to 0 for all x. This creates problems because when there are more than one powers that a certain number must be raised to produce a given number, we would have trouble deciding which one is the true output of the logarithm. Similarly, if a is equal to 1, b is equal to 1 for all x, which gives rise to the same problem as when a is equal to 0. A cannot be less than or equal to 0, so a must be greater than 0, and since a is positive, b, which is equal to a to the power of x, must be positive too. To see this for yourself, model the graph of y equals any positive number to the power of x in a graphical calculator. You may notice that the value of y gets closer and closer to 0 as x gets more and more negative, but it will never be precisely equal to 0, and therefore b is always greater than 0. The following formulas describe the four logarithm rules. We know from before that a to the power of x equals b is equivalent to x equals log base a of b. If we substitute the second equation into the first, we get a to the power of log base a of b equals b. So the key finding here is that the log cancels out when it is raised as a power to its base. Therefore, the equation xy equals x times y is equivalent to the equation a to the power of log base a of xy equals a to the power of log base a of x times a to the power of log base a of y. And by the rule of exponents, we know that it is equal to the following. If we equate the indices of a, we get log base a of xy equals log base a of x plus log base a of y. Analogously, the equation x over y equals x divided by y is equivalent to the equation a to the power of the log base a of x over y equals a to the power of log base a of x divided by a to the power of the log base a of y. And by the rule of exponents, we know that it is equal to the following. Again, we equate the indices of a to get log base a of x over y equals log base a of x minus log base a of y. And just like that, we have the first two logarithm rules. Before we begin with the next logarithm rule, let's remind ourselves that logarithms cancel out when they are raised as a power to its base. So we know that x is equal to a to the power of log base a of x, and also that x to the power of m is equal to a to the power of log base a of x to the power of m. But according to the first equation, x to the power of m is also equal to a to the power of log base a of x to the power of m. And by the rule of exponents, we know that it is equal to the following. Now, if we equate the indices of a in these expressions, we get log base a of x to the power of m is equal to m times log base a of x. Finally, we yet again begin by noting that x is equal to a to the power of log base a of x. So, log base b of x over log base b of a is equal to the following. Here, according to the logarithm rule we explored just above, the index within a logarithm can be taken out of the logarithm as a factor. So, after the log base a of x is taken out of the logarithm as a factor, and the log base b of a in the numerator and denominator cancels out, we are left with log base a of x. Therefore, log base a of x is equal to log base b of x over log base b of a. For the sum of an infinite geometric sequence, we are going to begin by expressing each term in terms of u1 and r using the formula for the nth term of a geometric sequence, just as we had done for the sum of a finite geometric sequence. Note that it is technically incorrect to have the term u infinity, but it will aid our understanding for now. Anyhow, as with before, we are then going to write down the equation for r times s infinity and subtract the second equation from the first. Again, all the terms will cancel out except for the first and last term, leaving us with s infinity minus r s infinity equals u1 minus u1 r to the power of infinity. Now, as you may have noticed, there is a condition on the formula that the absolute value of r is less than 1. So each time a number is multiplied with r, the absolute value of the output decreases. In other words, if we theoretically raised r to the power of infinity, it would be equal to 0. So we get that s infinity minus r s infinity equals u1. And if we divide 1 minus r on both sides, we get s infinity equals u1 over 1 minus r. The last formula we will be looking at today is the binomial theorem. As the name suggests, the binomial theorem gives a generalized formula for the expansion for powers of a binomial, or in other words, the powers of a sum of two terms. To get started, we're going to look at what happens when we multiply a plus b with c plus d. The answer is ac plus ad plus bc plus bd. And AC, AD, BC, BD are all the unique ways you can multiply a letter from the first bracket with a letter from the second bracket. If we now replace C and D with A and B, we get the expansion for A plus B squared, which is A squared plus 2AB plus B squared. Note that we have 2 of AB because when we multiply real numbers, the order at which we multiply the numbers doesn't affect the outcome. We could choose the A from the first bracket or the second bracket, but so long as we choose A from exactly one of the two brackets, we would create a term that is equal to AB. The first key to understanding the binomial theorem is to realize that even as we increase the number of binomials being multiplied, we still choose one letter from each bracket and sum all the multiples made as we try out every possible unique combination of which letter to choose on which bracket. So, when we try to expand a plus b to the power of n for some natural number n, we have n brackets of a plus b. As we either choose a or b from each of the n brackets, the possible multiples that can be made will be equal to at least one of the following: a to the power of n, a to the power of n minus 1b, a to the power of n minus 2b squared, all the way down to ab to the power of n minus 1, and b to the power of n, depending on how many brackets we're choosing a from, or alternatively b from. For example, to make an a to the power of n term, we need to choose a for all of the n brackets, and that can be done in only one way. So the coefficient of the a to the power of n term in the expansion will be 1. Whereas to make an a to the power of n minus 1b term, we need to choose a for n minus 1 brackets, or better so, b for 1 bracket. Since there are a total of n brackets, there are n ways to do this. We could take b from the first bracket and take a for the rest, take b from the second bracket and take a for the rest, and so on. So the coefficient of a to the power of n minus 1b term in the expansion will be n. Similarly, to make an a to the power of n minus 2b squared term, we need to choose b for 2 out of the n brackets. Since not choosing b means to choose a, This automatically means that we're choosing A for n minus 2 out of the n brackets. So the coefficient of the a to the power of n minus 2 b squared term in the expansion will be equal to the number of different ways we can select two special brackets from which we will be choosing b from. Now, once we take the time to process that, we have a pleasant surprise. There is actually a formula that gives us the number of ways you can choose R objects from a pile of n, and it is right here. NCR equals n factorial over r factorial n minus r factorial. So NC2 gives the number of different ways we can choose two brackets from a pile of n, and therefore it will be the coefficient of the a to the power n minus 2 b squared term in the expansion. In general, to make the term a to the power n minus r b to the power of r, we need r brackets to choose b from, and there are NCR different ways of selecting those r brackets in a total of n. Therefore, the coefficient should be NCR. For reference, 1 is equal to NC0, n is equal to NC1, and the coefficients that should go into these blanks are NCn minus 1 and NCn, or alternatively 1. And that there is the binomial theorem. Note that the C in NCR is called combination, and we will go through the derivation of this formula when we cover the HL only section of topic 1. In the next video, I'll cover the formulas from the topic 2 functions, SL and HL section. I plan to go through all the SL and HL sections first, then the HL only section, and eventually the IB Mathematics Applications and Interpretation formula booklet. So stay tuned if that is of interest to you. I hope that helped.